Hello, everyone, and welcome back to Creation Myths. Folks, we are back talking about Dr. Rob Stadler and the 2016 paper Statistical Evidence for Common Ancestry Application to Primates. Because it happened. After saying he was done with this conversation.
And with this, folks, I think our discussion, we've had like 5 back and forth videos at this point. I think our discussion has run its course. Unless something revelationary comes up, Dan and Erica, you're welcome to have the last word.
Dr. Rob Stadler decided to give it one more try. And while I am happy to report that he is less wrong than he was before, I am also disappointed to report that he is still wrong. So let's talk about it. On August 10th, 2025, Dr. Stadler released another video about this paper and me and Erica Gutsa-Gibbon on James Torr's channel. This was in response to this video with Erica, wherein we went over that paper, the 2016 paper, and specifically its methods in what some people might call excruciating detail, which is fair enough. In that stroll through phylogenetic methods, we pointed out some very significant problems in the arguments Dr. Stadler has been making. Specifically, how he leans on this one quote from that 2016 paper. The quote is, "We assume that each family ancestor at its origin acquired character states at each character independently of all other family ancestors." Dr. Stadler had, up until this most recent video, claimed that this meant that when Baum et al. Generated the sequences for the family ancestors in their test of the FSA model, family separate ancestry, they generated those sequences randomly and without any correlation to each other, so no pattern of similarity between those family ancestor sequences. Dr. Stadler repeatedly characterized this as a straw man of a common design argument, since the family ancestor would of course have been created with built-in nested hierarchical patterns of similarity. For example, here's just one clip of him articulating that point. That assumption requires a justification, but that's not the point for this video, so just don't worry about it. Just leave that one to the side. Don't worry about it. The important thing for what we're talking about right now is that as of this most recent video, which is to say the August 10th, 2025 video, Dr. Stadler now understands that the methods used by Baum et al. Did not involve generating the actual ancestor sequences for each family. He has now revised his characterization of the permutation tail probability test. This is how we did it, using a figure that looks a whole lot like one that I drew. He acknowledges that the line we quoted earlier actually means that they used random permutations of the sequence data to generate the distribution of possible tree lengths. Because again, I'm not going to go through all the methods right now, but if you want to go to that longer video, link down below, you can see how we talk about maximum parsimony as the standard we're using to evaluate phylogenetic trees. It just means how short is the tree, where shorter means better because it means fewer mutations, right? So that's what we're describing here, okay? And now Dr. Stadler is correctly interpreting what this method actually does. So that's great. He's accurately describing the methodology and has, in so many words, acknowledged that his previous argument was wrong. He doesn't say that outright, but well, just take a look. You can just watch this.
So I'm going to start off, maybe this will surprise everyone, but I'm going to start off by actually making a concession here. When I speak of the forest of life, and you just saw all of this here, and I make the statement, no correlation structure at the start of life. Well, I know it turns out that in the paper by David Baum, which we just showed, the statistical ancestry paper, he did not literally derive the DNA at the start of life. So he didn't actually try to derive exactly what the DNA was in each of these kinds at the start of life. I get that. But if we want to get into the details and get more technical and more accurate, you could say, about that statement, let's get into that. And right now, I'm just going to give a little thumbnail overview of some of the details of this paper, and then we're going to go a little deeper. So I want to start by just giving an overview. So what they did in the paper is they randomly generate DNA for each family. So they literally take a random number generator and make up DNA for each of the families. And then from each set of that DNA, so one DNA for each family, so it's like a matrix of families and DNA code. For each matrix they generate, they derive the most parsimonious phylogenetic tree, which is a way of trying to connect these families together as if there was common ancestry. And they do that 1,000 times to arrive at a distribution of the type of correlation structure that could have arisen by chance alone. So they're trying to see what chance alone could provide as far as a nested hierarchy between the different families. And we'll get into that more. I know this is kind of technically challenging. Then here comes the big straw man assumption. Then they assume that under this common designer model, the designer of life would not have provided any more correlation structure between families than could be provided by chance alone. And that's the big key assumption we're going to be focusing on. So in other words, they assume negligible, not zero, but really, really close approximation to zero, negligible correlation structure between the families. And that happens to imply, when you think about it, that happens to imply that there's negligible correlation structure at the start of life, even though they didn't literally find the DNA or use DNA at the beginning of life. So basically, it sums up, they basically assume there's no correlation structure at the start of life, which is my statement here. So if I want to be more accurate, this original statement that I made, and I've made it many times, I could have made it slightly more accurate, but much less understandable if I had changed these words here. Instead of no correlation structure at the start of life, I could have said, the designer provided no more correlation structure between families than chance alone would have provided. That's more accurate, but a lot less understandable. And so that's why I went with this one.
That's about as good as you're ever going to get, so I'll take it. Thank you, Dr. Statler. To be clear, this means that his previous argument was completely wrong. I want to be clear about that so everybody hears it. The entire argument was that Baum et al. Used a straw man argument for their separate ancestry because of the random ancestors. They weren't actually testing how a designer would have worked. The designer would have built in some pattern of similarity, and since Baum randomly generated each ancestral sequence, that was a straw man of the common design hypothesis, so it's not a valid test. He said this over and over and over. But Baum et al. Didn't randomly generate family ancestors, because they didn't generate family ancestors at all. And we're all on the same page with that now, which is great, because it's good to have an accurate understanding of the papers we're talking about, and it's even better to start with an inaccurate understanding and then revise your understanding to make it more accurate. Changing your mind to go from being wrong to not wrong is great, and that's what we're seeing here, right? Dr. Statler was wrong about this test and how the actual method works, and now he's accurately presenting how these methods work, and that's great. And it also means that his previous argument is completely invalid because it was based on a misunderstanding of these methods. So now we're going to move on, because all of that we just talked about covers the less wrong part of the video, and now we're going to get into the still wrong part of the video. Dr. Statler has two new critiques of this paper, and we're going to focus on the second one. So Dr. Stadler's second new argument here, and again, to be clear, this is a new argument. We've abandoned that original, it's a straw man argument. Now we're making a much narrower argument about the actual statistical methods of this test of family separate ancestry. His argument here is that 1,000 samples isn't enough to accurately characterize the distribution of tree lengths given the number of trees that are actually possible. So he's saying 1,000 is not a large enough sample size, and here's Dr. Statler making that argument, so you can just watch him do it.
So we're talking about the Perlman data. This shows that when they talk about using the PTP test, they're considering 16 families, and in each family they're considering DNA of length 34,860 nucleotides. So when we say that they randomly generated DNA as part of the PTP test to derive this distribution down here. They did 1,000 draws of 16 times 34,860 random DNA nucleotides. That's how the test was run. So let's do just a little bit of math here. Each nucleotide has 4 states. Could be an A, a C, a T, or a G. So they're talking about a distribution that has four different states raised to the power of 16 times 34,860. To try to put that into more convenient terminology, that would be a number 1 followed by 335,804 zeros. That's how many possible random draws from this data you can have. This is an incomprehensible number. It's just impossible to understand that. Let me try to put it in perspective. If you took every computer on the planet Earth, every computer, and you set them to one task, which is to generate randomly this 16 times 34,860, and you allowed those computers to run for 14 billion years, even 100 billion years, you would not even come close to beginning to test every possible permutation, every possible configuration. By doing this Monte Carlo simulation and just drawing 1,000 samples, 10 to the 3, not 10 to the 335,000, what they're trying to do is get a feel for the distribution of what chance alone could produce, to get a mean value and a standard deviation so that they can apply a normal Gaussian distribution to this and get a feel for what chance alone could produce. And in that case, it's a very tight distribution, and genomes with almost no hierarchical structure are going to vastly predominate. Genomes with any degree of hierarchy or correlation are what I call here impossibly rare, basically zero, near zero. You're not going to see them. It certainly does not in any way provide the best case scenario for family separate ancestry.
The first thing I want to point out here is that this is basically one of the arguments I proposed he could make in that earlier methodological video, that he could basically argue that the distribution of possible tree lengths that was generated by Baum et al. Is wrong. Here's that clip from my video with Erica, where I'm kind of presenting this as a potential counter argument. So check this out. Here is my attempt to steelman Dr. Stadler as hard as I can. And Rob, if you see this, let me know if this is what you're actually going for, right? So this is the most generous interpretation that I can come up with here, right? His critique is that the randomized data are not generating a realistic distribution for the separate ancestry hypothesis, because the actual process of creation of these separately created groups would either, we got two options here, right? Either A, it's going to result in a stronger artificial phylogenetic signal, i.e. shorter trees, right? The distribution was wrong because it didn't find trees that it should have found, right? That's one possible critique here. That distribution, for whatever reason, did not find the optimally short trees. Now, option A that I said, right, his critique is that the process of creation would have resulted in a stronger artificial signal than we actually get, right? That is begging the question, and I'm using that in the correct sense. He is assuming the conclusion he wants, saying that distribution is wrong. There are actually data points that are part of that distribution that you didn't find, right? And if that's the case, then I invite Rob to show that that's the case computationally. Pick up the baton, you have all the methods, generate your own distribution and show that the range, the minimum on that range that we just talked about should be a lot lower, right? Show that that's the case. You could do that. Publish that paper. That'd be awesome. Show us that that's the case. Now, please note that I said if he thinks that's the case, he needs to show it computationally. And I repeat that here. Dr. Stadler, if you think the distribution that was used for the comparison in the PTP test is not representative, correct the calculations and show the correct distribution. But there's a problem. Rob's numbers that I just showed in that clip a minute ago, those numbers are wrong. The way the PTP test works is it involves permuting ancestral and derived states for each character. And since we're working with DNA sequences, each character refers to each nucleotide position within that sequence. And each character state refers to which nucleotide base is actually there, A, T, C, or G, right? So when we're talking about ancestral and derived states, we're saying, okay, based on the phylogenetics, the ancestral state, the old version of that site at site, 6,192 or whatever, right? That's an A. Anybody who has an A, that's the ancestral state. If you have a G, that's a derived state, right? That's a new thing, that's a mutation that deviates from that ancestral state. So for each of our 16 taxa, because we're using families within primates, we're using 16 families, one sequence per family to do this test. So for each of our 16 sequences representing each family, we're going to, for site number 1, we're going to tally up ancestral versus derived for all 16. We're going to shuffle them, and we're going to reassign them. So you either start with the ancestral state or a derived state, and you're going to be randomly assigned either ancestral or derived. But very importantly, you're keeping the number of ancestral and derived states the same for each site. You're just shuffling within each character the assignment of the character states, ancestral or derived. Right? Now, this is apparent from the text of the 1989 paper that Baum et al. Referenced for this technique. You're not going to get this directly from the 2016 paper. You have to go to their reference. And the relevant passage is this. And it reads, real data sets can be made to have no phylogenetic information by randomizing the character state assignments within characters. Such randomized datasets will maintain all the characteristics of the original characters in terms of the number of apomorphic and plesiomorphic states of characters. And those two words, apomorphic and plesiomorphic, just mean ancestral and derived. So in other words, for each character, for each nucleotide, you take whatever state, whatever base it is in each sequence, and then randomly assign those states back to the 16 taxa. Now, this can be a little bit challenging to understand conceptually. So by analogy, I want everyone to think about it like shuffling and dealing playing cards. Right? Let's say we have 4 people and they each get 10 cards, right? And they're going to get those 10 cards in order, right? Number 1, number 2, number 3, all the way to number 10. So they have 10 cards that we can think of as card number 1 to card number 10. And we want to look at the pattern for each of those 4 people of diamonds, hearts, clubs, and spades. We want to know the pattern of the suits as you go down your sequence of 10 cards. Now, the way Dr. Stadler presents this is that each person is ditching those 10 cards and getting 10 new random cards, each from a new shuffled deck. We're just randomly generating 4 new sequences of 10 cards, right? And they're all completely independent from each other. It's separate new shuffled decks where all the cards are present. Any possible sequence is possible for each of those 4, right? That's how it is represented by Dr. Stadler. But what we're actually doing is going card by card from 1 to 10, having each person hand in the card, mixing up the 4, and then redealing them out to each of the 4 people. So for each site, 1 through 10, there are going to be the same cards in play, the same mix of diamonds, hearts, clubs, and spades, just randomly assigned. Right? So for card number 1, everyone give me your number 1, the top of your deck. I'm going to mix those 4 cards up, and I'm going to give them back to each of you randomly. Maybe you got the same card, maybe you got a different card. Card number 2, give me your 4 cards number 2, I'm going to mix them up, and I'm going to give them back to you, card number 2. That's how we're permuting the data. Now, a really important aspect to this is that for sites where there's no variation, say all 4 people have a club, for example, this permutation doesn't change anything. Say for site number 4, everyone gives me a card that's club suited, right? So I get 4 clubs in my hand and I mix and match and I shuffle them up and then I give 4 clubs back, where for site number 4, everyone's going to still have clubs, right? I haven't changed anything even though I've permuted the data, right? Because the thing that you're randomizing is uniform for that particular site. For sites with limited variation, say of the 4 people, you've got 2 hearts and 2 spades, there are only 2 options you're going to get, not 4, right? I'll take those 4 cards, 2 hearts, 2 spades, I'll shuffle them up, I'll give them back to you, and you can either get a heart or a spade, but you're never going to get a diamond. And importantly, once both of those spades are assigned, a heart is the only option, right? So the number of options you have is much more limited than how Dr. Stadler presents it in his description. But that's how the permutation in the permutation tail probability test works. So Rob's calculation here, just in terms of the number of possibilities, is way off. It's way too high because, again, you're not just generating independent random sequences for each of your 16 taxa. You're permuting the data as they exist, keeping some important parameters of that data as it is. So there are far fewer options than Dr. Stadler represents. And Dr. Stadler makes a very important conceptual error here. Look at how he describes Baum et al. Sampling. See how he says genomes, right? We're calculating the number of genomes. We're talking about how many genomes they sampled. They didn't sample genomes. They sampled trees, or more precisely, they sampled tree lengths. And that matters because there are different combinations of sequences that will have equal or near equal tree lengths. All of this is to say that Dr. Stadler's calculations here are incorrect. The argument he is making is that the distribution that Baum et al. Compared to the actual data, that randomized distribution of tree lengths, is not representative of the actual range of tree lengths. And Dr. Stadler, please correct me if I'm misunderstanding your argument, but it sounds like you're saying 1,000 sequences or 1,000 samples is not enough to accurately construct that distribution. So when you're comparing the distribution from the randomized sequence data compared to the actual data, the fact that they're so far apart is not valid because you're not accurately representing what that range of possibilities in the data actually looks like. And if I can say it in a much simpler way, I believe Dr. Stadler's argument is that that distribution should be a lot wider than it is, or at the very least, it should have a longer tail on the low end, right? There should be many more sequences represented in that distribution that have very short tree lengths, right? That's, I believe, the argument that Dr. Stadler is making. Again, Dr. Stadler, correct me if I'm wrong, but that is how I am understanding your argument. And in order to make that argument, you need to have the right numbers in order to calculate what that distribution actually looks like. And the numbers you showed are not going to generate the correct distribution because those numbers are wrong. But having said all of that, I do want to point out a very important and I think very positive aspect of this new critique of the paper. And one more time, I'll point out, yes, this is a new argument from Dr. Stadler. This argument is a lot better than the original because it's a very narrow statistical argument, and that makes it testable. So here's how Dr. Stadler can actually demonstrate that he's correct about everything he's saying about this test of family separate ancestry. There are 4 things he needs to do, and if he does all 4 of them, then he can actually test his hypothesis here. So 1, he needs to correct his numbers as I just described, right? The numbers he provided are wrong. So he needs to fix those numbers in terms of the permutation technique, the randomized sites, the number of potential sequences in trees without conflating those two things, sequences versus trees, to get the total number of possible trees correct. Number 2, he has to show mathematically that the number of samples used in the paper is insufficient to accurately represent whatever that distribution is. Basically, he has to show that there's a disconnect between the sample size, 1,000, and the actual number of possibilities. Is that sample size too small to accurately represent that distribution? Number 3, he has to show mathematically what the correct distribution would be. In the paper, they provided minimum, median, and maximum. Calculate and provide the correct numbers. And then finally, he has to calculate the corrected p-values and show that the observed tree length, the most parsimonious tree based on the real data, is not an outlier. Show that it's actually part of that now correct distribution. If Dr. Stadler does those things, and the p-values indicate that the observed level of parsimony is not an outlier of that range, of that distribution, I will concede the point and publicly issue a correction saying that this analysis in the Baum 2016 paper does not disprove family separate ancestry. I love this. We have a specific hypothesis. Actually, we have two specific hypotheses and specific predictions that we can now test. I predict the observed values will be significant outliers. That's what the paper shows now, and I think the methods in the paper, as they exist, are pretty much fine. So I think if you were to correct those methods, have a wider distribution, whatever it is, I think the results are pretty much going to come out the same. Dr. Stadler, I'm going to presume, would predict that the real data won't be an outlier. It will be much closer to that distribution, and it'll be a non-significant p-value. That's pretty simple. If Dr. Stadler wants people to come around to his side, he can simply test that hypothesis and show that his predictions are correct. That's how science works. Ball's in your court, Dr. Stadler. This goes back to my problem with Dr. Stadler's book, The Scientific Approach to Evolution. In that book, he lays out his criteria for high confidence science, and he has referenced those criteria in, I think, every video in this series as we've been going back and forth here. But never once in that book does he mention hypothesis testing. I don't know why that's omitted. That's the whole thing with science, right? You generate a hypothesis, you test the hypothesis. If you make accurate predictions, that is a point in favor of your hypothesis. Well, now we're hypothesis testing. He's revised his arguments. He's corrected at least one major error he's made. He's revised his arguments. Now he's making a very narrow statistical case about the techniques in this paper, and he can show mathematically that the conclusions of the paper are wrong by correcting their math. Make your predictions and show that your predictions are actually accurate. This is what science is all about. Welcome to the party, pal. And that's where we're going to leave this one. Like I said a minute ago, the ball is in Dr. Stadler's court. He has articulated a specific critique. He has, in effect, made a hypothesis, and now I invite him to test that hypothesis. And I, for one, am really excited to see him do that and see where the numbers lead. So thank you all for watching. Hope you all found that enjoyable and informative. Please remember to hit the like button before you go, leave a comment, subscribe, share the video, and if you are so inclined, please consider supporting me by becoming a channel member. As always, don't get fooled.